Thank you very much, Dr. Apicitoli. Now gives me some great pleasure to invite to the podium our keynote speaker, Dr. Philippe. Dr. Philippe is the HPC Director for Intel EMEA in the AXG Accelerated Computing Systems and Graphics Groups. He looks after the Intel EMEA HPC revenue and manages the team of HPC solution architects in EMEA. He works closely with the large HPC AI end-user customers and with leading OEMs and HPC AI ecosystem partners to define and build the HPC AI solutions, meeting the growing demand for application, performance, and power efficiencies. These solutions include not only the processing elements, but also the interconnect, including Intel networking solutions, the storage, Intel tools, compilers, libraries, etc. Dr. Philippe has been with Intel for over 28 years and has been in various positions in technical support, technical sales, and he has managed several teams and groups in technical pre-sales. Dr. Philippe holds a PhD from Grenoble, France in computer science, automation parallelization, and distributed memory supercomputers, and applied mathematics, cryptography. He owns 2 patents in Japan on automated parallelization techniques. With that said, I'd like to welcome Dr. Jean to the podium. Keynote speaker. Thank you, sir. Thank you.
Good morning, everyone. I'm Jean-Laurent Philippe. I'm the director for HPC at Intel Europe, Middle East, and Africa, and I'm very honored to be here. I would like to start first with a small address to the young people here, because how I started is very interesting. I was 14, and my parents bought me a small calculator, a programmable calculator. And I already liked integer numbers. And there was a contest in Europe, or at least, yeah, in Europe, that was how many instructions can you minimally use on that programmable calculator to calculate the GCD, the greatest common divider or denominator of 2 integers. And for my colleagues at HPE who are here, at that time, that was an HP41C. Those old people with gray hair probably remember that. And I played with that, and I worked on it, and I brought the number of instructions down from 8 to 7 for the whole program. So with that, I started. And then I played with the integer numbers in my PhD. I did cryptography. And then I'm here because cryptography uses HPC, and I'm still passionate about HPC now. And I'm sure that I will be until I retire. So just to tell you, if you have a passion, follow it. It will pay off. With that, now, I'd like to tell you a little bit more about where Intel is bringing HPC in the future, how we are going to help democratize the usage of HPC, and how we will help sustainable development, especially of applications. Intel has a mission, and the mission is we create world-changing technology that improves the life of every person on Earth. I know it's a huge game, it's a huge plan, but at least it is what I can think of every morning when I get up. What I will do today will help get the world better in some ways. Before I get into the deeper dives of HPC, I'm going to tell you a little bit about Intel, because Intel is reinventing itself. Intel has been known for doing CPUs, and you probably have our core processors in your laptops. Those who do HPC also may have Xeon processors in their systems. So we are known for that. But at each time we come with a new solution based on a CPU, we also do all of the ecosystem enabling that goes with it so that it is immediately usable and you can take advantage of it. This means that we work on the compilers, we work on the drivers, we work on the software that will be taking advantage of the hardware that we are providing, and that the ecosystem partners like our OEMs use to put in the systems that you use. So what we do is we design the hardware, we manufacture it, and we package it and we deliver it. But we also work on making sure that we prepare for the future. Our CEO has been very clear that there is so much that we need to do that we have to have some guiding principles. We know that now computing is important, but computing, as Dr. Happy Sitoli said, without data doesn't work. So we need to get the data. Data requires to be communicated. So there needs to be communication between the entities that store, compute, and deliver the results on data. That's the pervasive connectivity that needs to be everywhere. It goes from edge to cloud, and now we see artificial intelligence everywhere, plus the sensing. So all of this is driving where the world is going. Intel is just providing the building blocks for all what you are using on a day-to-day basis. How we win is by basing everything on standardization. And there comes the idea of democratization. Because when it is standard, then everybody can use it. It's interoperable. So that's very important. We want to go and win by developing solutions or ingredients and building blocks for solutions that are based on standards, on open and secure standards, and that are usable, I would say, as easily as possible. So as you can see to the right, we are developing the architectures, we are manufacturing in our foundries, but we are also bringing a new solution for the manufacturing environment. And that's the one which is at the right here, IFS. I'll talk about it in a second. So that here you can see all what Intel is doing in terms of business development. We do the CPUs for the laptops and desktops and workstations and servers and HPC. And the group that I am in is AXG, Accelerated Computing Systems and Graphics. Our goal in this group is to become the #1 provider of accelerated computing. We are on the path to it, and I will show you how we are going to get there. But the way we are doing it is not only by designing the architecture of the solution, we are also planning to be more open in terms of foundry. So we have created under IDM 2.0 that you saw on the previous slide, an entity called the Intel Foundry Services, where we are not only opening our fabs to anyone who wants to manufacture in it, but we are also using other fabs from other suppliers like TSMC for getting the best of each and every solution for each and every aspect of a CPU, a GPU, or any component that we will be designing and bringing to life. Why do we need to do that? Because there is more and more need for simulation in all aspects of the industry. Yes, everybody is looking at the top 500 and who will be the biggest or fastest or highest performing supercomputer in the world. But running a lean pack is one aspect, especially for machines that are costing a large amount of money. What makes really sense is how can the community benefit from it by doing some simulation, by helping the industry. And I'm very, very, very happy to see that the goal here in South Africa is really to help the industry develop, to help the research go further, and to prepare for the next generation of young people to be there. The problem is that when you have a supercomputer, it runs HPC, but it also has to run AI applications. So it's an environment that is really key in terms of all of the things that can be run on there. And the workloads are of very various types. Some are compute bound, meaning that there's never enough computing performance in the system to crunch all of the data, because the data is here and we don't have a problem to getting them there. But there are also some applications that are memory bandwidth bound. That means that the data is actually the bottleneck to be crunched. So once we can find a solution to help this bottleneck to be resolved, then that would help a certain number, as you can see here, between 30 and 50% of the applications to run faster. And it's pretty costly to use a computer that is memory, an application which is memory bandwidth bound on a computer that is so powerful that it is starving, that it does not have enough data. So we need to help with that. So we have looked at what the applications look like. And you can see a kind of matrix on the right-hand side with a vertical axis, which goes from memory bandwidth bound to compute bound. And on the x-axis, capability systems for time to solution to capacity system in terms of throughput. And you can see that in this corner, that's compute optimized. Here it's memory bandwidth bound. And here there are the frequency optimized applications. We want them all to run as fast as we can for many reasons. People want to get their results ASAP. That's always been the case, one. Second, if you run an application and it takes much more time than the optimal implementation would be, then you are not sustaining the energy. So you need to find a way of reducing the time to solution so that we save this Earth in terms of energy. Which architecture can meet all of these criteria? There are many routes to the summit. There's the CPU route, which in the past worked on increasing the number of cores and the frequency. There's the GPU route that helped with offloading the data parallel kernels, and that has this high bandwidth memory that can feed the data to the cores much faster than on a CPU. So how do we get there? There are some obstacles on the CPU side. mostly the memory bandwidth. It's never enough, and that's what we call the memory wall. I'll talk about it in a second. And there are some obstacles on the GPU side, and I'll talk about it a little bit later. What is this memory wall that I'm talking about? You can see the blue line, which shows the growth in terms of compute capabilities in the past about 10 years. The performance of each core has increased a lot and quite steadily over the past 8 years. However, you can see that the memory bandwidth per core has stayed flat, which means that the cores might be starving for data. How do we fix that? We work on the memory bandwidth. And on the GPU side, the problem that we see is that there's not enough memory capacity to hold all of the data to feed all of the cores. And the problem also that we are seeing is the applications need to be at the moment a little bit too much customized to take advantage of the hardware. So as we are talking about democratization, we absolutely want that the applications that have been written by experts in their domain can be run on any of those infrastructures with the different architectures without having to cope with some of those obstacles. So at the moment, what is a typical HPC system? It's a group of nodes that are connected to each other, and on the nodes, there are some CPU capabilities and GPU capabilities. What I'm showing here is that on the CPU side, we have low bandwidth, but a high memory capacity. And on the GPU side, we have a small memory capacity and a super high bandwidth. So for the application that can take advantage of a lot of compute with not so much memory, that's great. But at the moment, it means that the CPU, which is hosting the application, needs to transfer the data back and forth between the CPU and the GPU. And as you can see, the size of the pipe here is pretty small, which means that you need to identify which applications can have a big offload part that can run on the GPU faster. But you have to take it into account the time that it takes to send the data and to retrieve the results. And then you look at your total time to solution. And if you have a solution that is shorter than without the GPU, then go for it. Great. But we want to make sure that we are not going to pick and choose a few applications, identify an architecture that would work for it, and claim victory. Great, we have a solution for this and that and this other application. We want no HPC workload left behind. So not last week, 2 weeks ago, at Supercomputing in Dallas, we have announced the brand names of 2 new solutions from Intel, the Xeon Max series and the Intel Data Center GPU Max series. And they are solving the issues that we have just talked about. I will first focus on the Xeon Max. And the Xeon Max, as we showed earlier, is solving the issue on the CPU side with not enough memory bandwidth. It used to be called Sapphire Rapids with HBM, and now it's called Xeon Max. It has, well, actually, it is easy to understand it because it is just a normal Sapphire Rapids with HBM stacks on the side. Wow, okay, great. So that means that it is the same socket. So that means that in terms of sustainable development, the same platform for Sapphire Rapids and Intel Xeon Max. By the way, Sapphire Rapids is Intel Xeon 4th generation scalable processors. So if you allow me, I'll call it Sapphire Rapids because that's a little bit easier. So Sapphire Rapids and Sapphire Rapids HBM share the same platform. Great. Sustainability in terms of development is important. For the people who are running the data centers, that means a single image and a single hardware, so that's pretty good. And it brings 64 gigabytes of HBM. Where is it here? 64 gigabytes of HBM. So that means that we have a little bit of additional memory, but we can still have DDR. And this memory, this HBM memory, runs at about 1 terabytes per second, compared to the memory on the Sapphire Rapids, which is significantly slower, and I'll talk about it in a moment. Sustainable development, democratization. Okay, how do we use it? Okay, do I need to rewrite my application? No, not at all. You take your application. If your application uses less than 64 gigabytes of memory per socket, then you don't even need DDR. You launch your application and it will run because the OS is knowledgeable about the HBM and knows how to cope with it. Now, if your application needs more than 64 gigabytes of memory, which is on the HBM, then you can add the DDR5 memory from 16 gigabytes to terabytes of memory on a node. And in that case, you can use it either in cache mode. In that case, you have the CPU cache levels, level 1, level 2, last level cache called also L3. And then the HBM is considered by the OS as a cache to the DDR. Again, no need to change the application. The OS will be capable, Linux versions, absolutely, are capable of understanding that, and they will then use the HBM as a cache. Now, as we all want higher levels of performance, then we can run and choose at boot time the CPU to run in flat mode, in which case the HBM and the DDR memory capacities are two different regions, and then you have to choose where you store your data or where you load your data. And of course, you want to use the HBM for the data, which you will be using more often. So that makes it pretty easy to use. How does it go in terms of performance per watt? We are taking here a public reference, which is the CPU from AMD 773, the Milan X CPU, that has the largest cache and the highest level of bandwidth. And we are taking the HPC benchmark, which is a mix of compute and memory bandwidth. And you can see here that with HBM only, then we are reducing the power significantly. And if you use some DDR5 on the Xeon Max, then we are getting a little bit higher, but very significantly lower than other existing CPUs, based on the fact that the memory bandwidth is much higher. When we look at the comparison to the existing Intel third generation Xeon processors called Ice Lake, the 8380 here, then you can see that for LinPack, we get a better performance with Xeon Max, and on HPCG and on Stream, as I told you earlier, we are seeing a significant boost in performance. 5x for Stream, about 4x for HPCG, and about the same when you compare the same to competition. So that means that for the applications that are memory bandwidth bound, then we have a solution that will be reducing the time to solution, that will be reducing the energy cost of running the application by up to 4.8x in terms of performance. But you can see that on real applications, it ranges from a 50% performance increase to 5x, 4x, 3x, and in average in the range of 2 to 2.5. That's really worth it. And when we compare that to the current generation of Intel Xeon processors on those applications, like weather forecast, life science, manufacturing, and those, then there is a significant performance increase, and therefore a cost of ownership which is decreasing. That's great, and let's look at some specific applications, in that case, manufacturing. On Altair AccuSolve, you can see that from the previous generation of Xeon, we are getting 2.5x performance increase. That's also interesting to see, hey, if I want to compute the same workload with the same data set, how many nodes do I need? How many CPUs do I need? How much power will I need? And you can see that from the previous generation here of Intel Xeon third generation processor Ice Lake to Xeon Max, then we are reducing significantly from 4 systems down to 1, from 64 DIMMs, because there are 4 systems, down to 0, and decreasing the total power needed for running the application by a big percentage. We are not talking here about 5%. This is really, really big. Let's look at molecular dynamics. DeepMD. Here, 2.8x performance increase. Earth modeling system, and here we are talking about MPAS. 2.4x. Again, as I said, weather forecast and all that kind of applications. And the good thing is that a lot of systems will be available shortly from our esteemed OEMs who are partnering with us. And they will be available in the first half of 2023. They're all ready. So great. We are solving one of the problems going to the top, which is the memory bandwidth wall on the CPU. What about on the GPU side with the memory capacity and with the porting of applications? We have announced at Supercomputing, the brand name for the Ponte Vecchio GPU that you've heard of probably in the past. It is now called Intel Data Center GPU Max. And it's a series because there will be a second generation called Rialto Bridge that I will talk about. So here you can see that's an actual picture. There are 2 parts, 2 tiles that are equivalent and that include compute, memory, interconnect. So memory means L2 cache as well as HBM. And you can see here that it consists of 128 Xe cores. Xe is the code name for the architecture that is used in the Intel GPUs. It will have a peak performance of 52 teraflops FP64, and it can be connected to many other of their colleagues through Xe links. 8 per tile, which means 16 per Ponte Vecchio. And that will allow the highest density compute in a socket. And it also targets one of the issues that I mentioned earlier, which is there's never enough memory on a GPU. Here we are bringing 128 gigabytes of HBM2E memory, but we also have a huge L2 cache for up to 408 megabytes and a lot of L1 cache up to 64 megabytes. If you look at the impact of the L2 cache on an application, which in this case is a 2D FFT, then you can see that if you have 32 meg of L2 cache, then you have a certain level of performance. If you increase that L2 cache to 80 megabytes, then you get 6% additional performance. But if you go to the 408 megabytes that the Ponte Vecchio GPU is bringing, then you double the performance of the 2D FFT. So you remember my issue with the memory capacity on the GPU. Here, I'm talking about the L2 cache, but you also noticed that with 128 gigabytes of HBM2E, we are also bringing a new level in terms of the data that can be stored in that memory on the GPU. We are also bringing XE matrix extension so that we can have a lot of operations done in one cycle. I'm not going to read the data here, but this is really bringing the compute and memory solutions together in this GPU. As you know, simulations means that a lot of work is being done on the GPU, and then at some point in time, you want to see what you are computing. So we are bringing ray tracing, or we are bringing ray tracing capabilities directly on the GPU so that you can directly prepare the picture of what you've just simulated. Just an example of what the ray tracing capabilities of Ponte Vecchio are bringing. You can see here some rendering done for some movies or for typically the tokamak simulation and its visualization. So that means that you don't need to transfer the resulting data from the simulation back out of the system onto another node to do the rendering. You can do it directly on the node that is equipped with Ponte Vecchio. Great. Okay, so Intel is bringing a GPU. Superb. Okay, what is the programming language? Will I have to learn yet another language? And what do I do with the application that I have already developed on other GPUs? You remember what I said at the beginning? Intel wants to use as much as possible standards. So in that case, we have offered to the ecosystem the one API suggestion, which would be a solution by which applications can be developed in an environment so that then they can virtually any architecture. Of course, an Intel Xeon, an Intel GPU, an NVIDIA GPU, an NVIDIA ARM-based CPU, an AMD CPU, an AMD GPU, maybe some others coming in the future. Everybody talks about RISC-V or others. Okay, great. So that's the one API that we announced in 2019 in beta, and that has evolved to version 1, and that will be, we are on the 30th of November, so in December, there's the 2023 version of it. And that will bring a lot of new things and easy to use. As I said, it is really based on standards. Our goal is really to make sure that there's no need to learn something new. So the new release of the one API version for the Intel CPUs and GPUs is coming in December. It is based, as all of the one API standard, on SYCL, which is a language which is standardized. And we are bringing a lot of new tools to it It will be the first version of the One API version from Intel that will include the complete instructions support for Fortran. And I know that in some areas, I have a lot of customers who absolutely want to keep on developing in Fortran. But it's not only for HPC, it's also for AI. So TensorFlow, PyTorch are also well supported here. And for those who have some CUDA-based code, then we are bringing a tool called Cyclomatic that is translating source code from CUDA to SYCL source code. And once it is in SYCL, then it can be run on every of the architectures that I talked about earlier. For this GPU that is coming, Intel, as usual, is investing huge amount of money and resources to bring the mostly used applications directly on this GPU. By that, I mean that we are taking advantage of the features of the GPU in those applications. So we are porting them, and you can see a lot of them here on this slide. In terms of performance, comparing to the current NVIDIA solution A100, and I know that NVIDIA announced the H100, as soon as Intel can put our hands on an NVIDIA H100, we will update this slide, but so far we have not been able to purchase one, even if we are ready to pay the strict price for it. It's not easy. So as soon as we can do that, we will show the update here. But we are very, very confident that given the performance that you can see here compared to the A100, 2x on some applications, then you will see some really good performance of Ponte Vecchio against H100. Another example here is the virtual reactor simulation. And you can see here that we are showing between 30 and 70% performance increase on the Ponte Vecchio GPU. This GPU will come in 3 versions: a 300-watt PCIe card. And again, here, we are looking at democratization and sustainability. Not everyone will want the OEM version that I'm going to talk about in the next slide, which is requiring a certain level of cooling. Let's say it's better with direct liquid cooling, while a lot of people can put a PCIe card in their system and can work on it with 2 of them, up to 4 of them, and just work on the porting, on the evaluation, and on getting ready with their codes for the next generation. As I said, there are 2 other versions of Ponte Vecchio that are coming, and they are on an OEM form factor. And here they are a little bit higher in performance in TDP, total dissipated power, 450 and 600 watts. But they also come with more memory and with more compute capabilities. And then we also bring those OEM modules directly on a subsystem that is hosting 4 of them. As you can see here, this is the form factor, and you can see 4 of the OEM Ponte Vecchio modules on it that you can slide in to your system, and that will be hosted by Xeon CPUs. Again, you've heard of Ponte Vecchio probably because of the Aurora system, and I'll talk about it in a second. And we have a lot of designs work in progress with our partners that will be coming very soon, some now, some in the first half of 2023. So that's just a summary of what we are offering in terms of the Ponte Vecchio. In terms of performance, if you see here the LAMPS code using both the Xeon Max with HBM and the GPU Max, then you can see that if you run it on the existing Ice Lake processor and you move LAMPS to just the Sapphire with HBM, you get 60% performance increase. If then you add to it the GPU, but only with DDR, then you get about 6x, and then a 10x from here to here if you use HBM only with no DDR. So again, when you see this, then you think, wow, there's probably hope for getting more results or in a shorter time in the future at a decent cost of ownership, especially in terms of power. Or it can mean that people can do a lot more research and simulations doing that. Okay, superb. So we have solved some of the issues with Xeon Max, some of the issues with GPU Max. All this will come together in the Aurora system from the DOE that will have over 2 exaflops of peak performance. And in order to make sure that the data aspect will also be taken care of, there is a Deos storage subsystem attached to Aurora that will have over 6 tebibytes of, per second of bandwidth, using about 200 Deos storage servers. And you can see to the right that this means that hopefully the storage in that case won't be a bottleneck. We know that access to data is very, very critical. So I talked about Sapphire HBM, and you can see here that it is on this line here. I talked about the GPU Max, and there's a next one coming. And we also have some dedicated AI solutions with Gaudi, but I don't plan on talking about it here. And you can see that in the future, we will go to something that will be bringing together the best of these Xeon Max and GPU Max solutions. So let's talk a little bit about what's coming after Ponte Vecchio. I'll be fast. It's called Rialto Bridge. Greatly, it brings a lot more performance, but at a cost of development for the platform as well as for the applications, which is extremely low. Because although it will have different underlying system, the same form fit between Ponte Vecchio and Rialto means that you can slide out and slide back in Ponte Vecchio versus a Rialto in your system, which again makes it easier and more sustainable to reuse some of the hardware that was available until then. So we are at a stage where we have solved partially some of the issues that I talked about at the beginning. And we are now preparing for the convergence of those two solutions into what is called an XPU at Intel, CPU plus GPU integrated into one. Intel believes that a future HPC system will be based on integrated CPU and GPU solutions with high bandwidth memory into a same package, so that we solve both the compute barrier, the memory wall barrier, access to memory, coherence of data between CPU and GPU, which at the moment needs to be transferred over the PCIe bus, as I talked about a moment ago. And if there is really a need for more memory, then this packaging will be capable of being connected to some DDR solutions at that time, probably over a lower bandwidth protocol, but at least making possible to have larger data sets if we needed on this, let's call it package, or I don't know if we call it CPU or GPU, but on this XPU. The code name for this XPU solution is Falcon Shores. On the left, you can see that Falcon Shores can be only using x86 cores. In that case, that will be a Xeon type CPU with HBM. It can be equipped with GPU cores only. In that case, it's the follow-on to Rialto Bridge, GPU cores with HBM. Or it can be a mix of CPU cores and GPU cores with HBM. In that case, that's the XPU that I've been talking about. Great. But you also heard me talk about the future. The European Commission is clearly pushing RISC-V. We hear a lot about this. Intel has also announced a collaboration with Cyperl in the European Union, where Cyperl is a solution based on ARM. So when we think a little bit further than Intel, then why would we not put some non-Intel tiles or chiplets into that solution? That's something that we are really, really looking at. And if you look at the big pictures that I painted at the beginning with IFS, IDM 2.0, then that means that maybe those solutions could be manufactured at Intel fabs or at a TSMC fab or at another fab if they choose, as long as it uses some protocols to talk to HBM and to other tiles. And we know that there are plenty of protocols that Intel and the industry have been working on and that are fully available now, like CXL, like others, that we can use to get this communication between all of the parts. So, you know, there is hope for the future in terms of collaboration, convergence, and of course, reusability of all of the applications that are being developed now on Xeon or on GPUs, and that can take advantage of these architectures that we are bringing in the future. This is not for you to read and learn by heart. It's just my summary slide that shows that in the future, as usual, and as in the past, Intel is thinking very wide and broad and is looking at bringing a lot of solutions that are easy to put together, that are sustainable in terms of reusing some of the hardware and all of the applications that have been developed before that. And we are sure that the future is bright based on the Intel-based solution. So in order to prepare the future, I am pleased to announce that Intel is sponsoring the Best Student Award. And I'd like to call Dr. Happy Sitoli on stage to talk a little bit about it. While is coming up, so Dr. Happy Sitoli has already talked about all of the contests that are going on, the competitions for the students, but Intel is also bringing a best award for the best female student and an award for the best male student. Each of them are 80,000 rands, right? So there will be one female student getting 80,000 rands and a male student getting 80,000 rands. Through this next couple of days, with the rules that I would like you, Dr. Happy, to talk a little bit about, please.
Okay, thank you. Thank you, John Laurent. And I think here, students, you are here. So that's where the challenge starts. As we indicated, we would like to make sure that the best gets the best. And this is, the price is $5,000 US. So convert that, that gives you close to that figure that John Laurent just indicated. And to get to that, this will be open to the students in the student cluster competition. I know that there's big prizes for the datathon and cybersecurity that were announced. So this will be the one for the student cluster competition. So to get to that, it means that you have to start thinking about this, a one-pager that you are going to write about why you deserve this. One-pager. And the fonts, we said, don't go and try to put too much. So we are going to limit that to 14 points. 14. 12. Okay, 12. Harness is generous. So it's going to be 12. One pager, not more than one page. Why you deserve this? It's not just going to be the only decider here. The judges will be going through and looking at your performance also, technically, within the team. So those will be the two things. Motivate why you are the deserving students to get this, that one pager, including your performance in the team, that the judges will be doing the analysis, that combined. So you start that now, and the one pager should be in by tomorrow, that's Thursday, lunchtime, so that the judges can have access to what you have written, and it will be evaluated. And the announcement of the winner, obviously, will be at the awards function tomorrow evening. So the challenge starts now, and let us thank Intel again for giving this opportunity.